Hey AP Chem, my topic is kinetics, and the first thing I'm going to talk about is the collision theory. It states that when suitable particles of reactant hit with each other, only a certain percentage of the collisions cause any noticeable or significant chemical change known as an effective collision. In order to have an effective collision, particles must collide. Only two particles collide at one time for the most part, and they must have proper orientation in order to yield a chemical reaction. Increasing the temperature or the concentration can also increase the number of reactions and the number of effective collisions. In order to have an effective collision, the particles must collide with enough activation energy. This new collision product is at the peak of the activation energy hump and is called the activated complex or transition state. At this point, the activated complex can still either fall to reactants or back to the products. You can mark the position of activation energy on a Maxwell-Boltzmann distribution diagram, just like the blue line. When we increase the temperature to the red line, more molecules are energetic enough to achieve the activation energy, and more molecules react, and the overall reaction rate increases. A general rule of thumb is that the reaction rate doubles for each 10 degrees Celsius rise in temperature. Reaction mechanisms represent the sequence of bond making and bond breaking steps that occur during the conversion of reactants to products. The elementary step is a reaction whose rate law can be written from its molecularity. This is not true for the overall reaction order. Rate mechanisms and rate expressions are determined by experiment and must agree with the experimentally determined rate law. The slowest step is the rate determining step. This is the one that the rate law is based off of. A reaction intermediate is produced in one step but consumed in another. The rate expression of an elementary step is predicted from the stoichiometry of the elementary step as per this table. And this last step right here we won't see very often because termomolecular reactions are very rare. Here we have an example of an overall reaction and its rate law. We have to find which of the mechanisms is consistent with the rate law and with the overall reaction, as well as finding the intermediates. When we cross off all of the intermediates, which are produced on one side and consumed on another, so it's all of the red circles are intermediates, we end up with both mechanism 1 and mechanism 2 being consistent with the reaction because both have X2 plus XY on the reactant side yielding X2Y2. Here we see that on mechanism 2 as well. And for the slow step, the reactant is X2 and the rate of these reactions equals K times the concentration of the reactant of the slow step. And on both that is consistent. Now we're moving on to catalyst. Catalysis is the increase in rate of a chemical reaction due to the participation of a substance called a catalyst. Unlike other reagents in the chemical reaction, a catalyst is not consumed. They function by lowering the activation energy of an elementary step in a reaction mechanism and by providing new and faster reaction mechanisms. There are both homogeneous catalysts, which exist in the same phase as reactant molecules, and heterogeneous catalysts, which exist in a different phase than reactants, and usually involve gaseous reactants absorbed on the surface of a solid catalyst. There are three important classes of catalysis: acid, base, surface, and enzyme. Here we have an example of a catalyzed reaction and an uncatalyzed reaction. So we see the reaction pathway for the catalyzed reaction takes less activation energy to get to the end of the reaction pathway than the uncatalyzed reaction. Application of catalysis and kinetics is seen in biology. Biological catalysts are called enzymes, which are proteins with specific shapes. ATP synthetase is the most important enzyme in the human body. So death occurs when an organism runs out of ATP. Chlorofluorocarbons were used recently as refrigerants and as propellants in aerosol cans. They are relatively inert and remain in the environment for a long time. Eventually, they migrate into the upper atmosphere and are decomposed by high energy light. These chlorine atoms can catalyze the decomposition of ozone by forming a new reaction intermediate, thus thinning the atmospheric ozone layer that protects the Earth from harmful UV rays. Acid-base catalysis is an acceleration of a chemical reaction by addition of an acid or base, the acid or base itself not being consumed in the reaction. The catalytic reaction may be acid-base specific, as in the case of decomposition of the sugar sucrose into glucose and fructose and sulfuric acid. This is also an example of a dehydration reaction.